When talking about electrical potential energy, we first want to revisit what gravitational potential energy is. And that is if we take a certain object and put it a certain height above what we call the zero level, it will have a gravitational potential energy. Now, if I let that object go, the gravitational potential energy will go down, and the kinetic energy will then go up, and hence energy is conserved. So the total energy stays the same. It's just as one form of energy goes down, the other form of energy goes up. Now we can calculate that gravitational potential energy through the equation mgh. Can we simulate the same type of situation now only with electricity? And the answer is yes. If I take two plates, make one positive at the top and one negative at the bottom, we have an electric field here that goes from the positive to the negative to simulate that downward gravitational field that we had before. Now, if I take a positive charge, like a proton, and I place it within that electric field and let it go, it will move down just like this object up here moved down due to gravity. So there must be a potential energy associated with this object since it's doing the same type of thing as the other object up here with gravity. And so with the electrical potential energy, we instead of having mass have charge Q. Instead of a gravitational field, 9.81, we have an electric field. And instead of a height, we don't want to call this a height because we could as easily turn this on its side or turn this upside down. So in gravity, in gravitational potential energy, the gravity is always downward. But in electricity, we could also have it upward or left or right as well. And so we don't want to call it a height, we want to call it a distance in this situation. Now in this formula, we could call the zero height anywhere we wanted. We could call the zero height right here, or we could call the zero height down here. Usually we call it the lowermost part. So wherever it ended, that's usually where we call the zero height. Same thing in this situation, we can call zero height anywhere we want. Now there is one minor difference between these two equations, and that is there's a negative. And the idea of the negative comes from this idea that energy is conserved. Now, potential energy in and of itself is not a very useful value because we can call that zero distance or zero height anywhere we want. So instead, it's usually the change in potential energy that's much more valuable. And so this is the opposite of QE delta D, how far it is moving, its distance. And so we say that this change in potential energy should be negative because the potential energy should go down if energy is conserved. So let's see that it does indeed go down if we have a negative in front, and in this situation we had a positive charge. The electric field was downward, so that's negative. And the direction it moved was also down. This positive charge moves away from the positive towards the negative. Positive charge always moves in the same direction of the electric field, so that would be down as well. If we multiply a negative by a positive, by a negative, by a negative again, the change in potential energy becomes a negative number. In other words, the potential energy has gone down. But what if we were to instead have a negative charge and let it go? It increases in kinetic energy as it moves towards a positive plate, but will the potential energy go down? So let's see. We have the negative in front. It is now a negative charge, and the electric field is still downward, so that's negative. But in this situation, the electron moves up, so the distance it moves is positive. And a negative times a negative times a negative times a positive, again, is a negative down. So the negative in front ensures that the potential energy decreases when we let the object go. And as the potential energy decreases, the kinetic energy increases, and conservation of energy still is upheld. Now, if we look at this formula, we see that the charge times the electric field is the electric force. And the electric force is KQ1 Q2 over R squared. So we can replace this value with K Q1 Q2 over R squared. Now it's still times a distance, but we're using R for a distance now, so we'll use R again. And those distances cancel out. And so now we have a new equation if we're given 2-point charges, and that is K Q1 Q2 over R. Not R squared, just R. You'll notice that I left out the negative though, and that's because we don't need the negative. If I take two positive charges and place them near each other, as we let the charges go, the charges move away and the distance increases. And as the distance increases, the potential energy goes down. So it's already built in that the potential energy decreases as we let the objects go. So we don't need the negative on this equation. However, we are not able to choose wherever we want to be a zero distance or a zero potential energy in this case. It is already chosen for us within the equation. Because this R is in the denominator, as the R increases, the potential energy decreases. And as this distance approaches infinity, the electrical potential energy approaches 0 joules. So it's already told to us where the zero potential energy is. We can't just choose wherever we want like we could in the previous problem. So to review here, if we have these two charge plates, which is called a capacitor, by the way. If we were to move this positive charge from one point, from a lower point to a higher point, it would take work, and therefore this work is creating energy. Refer to that as the electrical potential energy. It's the change in potential energy that's important, and it's similar in a way to gravitational potential energy, as we had shown. The electrical potential energy, if we are given an electric field, we'll use this equation, the opposite of QED. If we're given two charges instead, then we'll use this equation, KQ1, Q2 over R. These are scalar values. We do not need directions with them. But make sure you're in the correct units. The electrical potential energy must be in joules, charge is in coulombs, electric field is in newtons per coulomb. Distance, no matter which equation, is in meters. But make sure, unlike the other ones, the other four equations that we use with force and electric field, we must include the positive and negative for the charges and directions in both equations. So these objects with charges do possess a potential energy, and this potential energy then can be converted into kinetic energy and work.